When I started out as a landscape architect in the 80s as a student in Germany, the Green Party got into power. And not into the power being running the country, but she got very powerful. It was a big impression in Germany to save landscape, to think about swaling, stormwater management, to think about all these aspects which to improve the environment. Actually, design went backwards a little bit, and design was seen second priority to saving the planet. So with that concept, when I was a student, I grew up and went to Edinburgh to study landscape architecture and horticulture there. And with that mission in mind, was my breeding ground. And the next stage was the 90s when I graduated, and people like Zaha Hadid or Daniel Libeskind, who were theorists and intellectual designers, used their graphics to come up with their own theories in design, which now they're actually practicing architects. On the same note were people like West 8, Adriaan Geus from Holland, whose work really exemplifies, particularly in landscape architecture, how visual graphics at the time in the 90s was really the message forward. It was also the time where, for example, the magazine Topos was created in Germany, which is now available in English. When it started out as a mission in the start of the 90s, it was only published in German, and it was the mission of the editor of this publication to actually make it an international journal. And it was with these kinds of images that journal actually got the respect. And I thought I'd just recap a little bit on this. Then we came into the 2000s, the change of the century, and there were people like James Corner who looked at, obviously with the reflection of the 90s, looked at graphic design, but they started to look at design in a much more holistic way. And the way the Fresh Kill site just outside New York exemplifies that in his competition proposal and winner is just one example I just wanted to show you as a sort of reminder. And the great thing about his work, apart from looking at it in different layers, he also put a time scale to his work. So for example, he used the work and looked at how a site could be used over the time period, how different parts of the site could be, through the involvement or the development of the plants, how these spaces would be changing and how then the site could be used. So he actually put a time scale on it, and there are diagrams. If you look and read up his stuff, you can actually see that. I always teach that my students. So he started actually, apart from looking at it from a graphical point of view, looking at the holistic system. And that was my mission, my vision, having practiced landscape architecture for 17 years, that it was not enough to do graphic work, to look at forms, but we really needed to start to understand the science and the systems holistically as a whole. So just to give you that as a background information. Then in the same period, the disasters intensified. We all know that, particularly things like Katrina, which in New Orleans caused the disasters. Even then, the then president, Bush, then also acknowledged that the environmental impact and the environmental message from landscape architects actually was important. And he was, and that was also an initiative for me when I was thinking about the research we were going to do. Today, I'm going to talk about these 8 points. I'm not going to read them down to you because at each point I'm having a slide. So we're going to look at these 8 points today and then to sort of set up my hypothesis. So this is the areas I'm going to talk about. I'm going to talk about Berlin, my time there. I'm going to talk about Vancouver and the establishing of the lab and the sort of start of the research we are doing. From there, we're going to Kelowna and then to China and Shanghai. We're going to look at some work we've been doing with figures, and then you can make up your own mind about these sort of ideas. But before I wanted to start out, I wanted to just talk about the consequences of urbanization, and that was the major issue which I wanted to tackle when I was going to Vancouver. And the graph here, the top left graph, shows that really well. We all know last year in 2008, it was the time when the urban population actually was higher was actually at peaking higher than the rural population. So the rural population now is on the decline, while the urban population is on the rise. And I put this into perspective of Vancouver just to give you some figures what that means. In the 50s, we had 50,000 inhabitants in Vancouver, and in 2036, we're going to have 3 million, and in 2050, we're going to have 4 million. So what do you do with all these people? Where do you put them? How do you feed them? How, particularly in a city like Vancouver, which is bordered by the sea and by the Rockies, which are literally not buildable on, because being in an earthquake-prone area, this has to be in the flat land. So densification, obviously, is the answer for this. And with this densification, we all know that has an enormous impact on the environment in the cities and on the environment of nature. So the urban destruction, and with that, the habitat destruction is still going on. I flew into Atlanta at Christmas and to change planes, and this is the sort of images I saw from the plane, and that made me aware again that we still have a long way to go, and we have to really learn to understand the systems, and that made me encouraged me as a landscape architect to go into the science side and really understand the figures, to actually persuade with the research we are doing the policy making of the governments. That's the real reason for the research we were thinking of. So we started to look at it more specifically. What is actually the impact on cities, and what does happen if the city gets all this imperviousness? Well, we know sewage overflow will happen. We're going to have flooding, and we will have a degradation of the water, which is the key issue. Food and water is going to be the key issue of this century. I'm quite sure about that. So my sort of vision was to study more in detail what we as landscape architects could do to mitigate this situation. And on the top right, I brought you this sort of typical diagram of a natural water cycle with no disruption. And when you have the disruption, in a very extreme case, that's what happens at the bottom right hand. So we try to find solutions to improve that. The next aspect we have, because of the urbanization, is the heat island effect. Everybody talks about it, but it is actually a very simple thing. I brought you these two graphs of downtown New York City. You can see here, if I get the pointer out, it doesn't work. It does. Here is Central Park. This map is the vegetation map, and this map is a heat map. And the bluer colors mean lower temperature to the pink colors. So everywhere where there is vegetation, there is a certain cooling effect of that vegetation of about 3 to 4%, meaning that the parks and the vegetation we have in the city is crucial for our future living, not just for the heat, but also for the stormwater reduction. So where did the ideas from the Greenskin Lab originate? And they came from my time being the landscape architect in charge of the Potsdamer Platz project here. And it was in Berlin, in the city center. This is the old east side, this is the west side. I'm sure a few of you have seen it. And I did that together with Herbert Dreiseitel. He was in charge of the lake and the water features, and we were in charge of the extensive and the intensive green roof areas. It was a project which went on for 7 years. And in 1995, this was quite a sort of cutting edge in the sense that the water we actually harvested on the project was used on the project. And I think that was also for me, when I was a practicing landscape architect on this scheme, the first time I experienced scientists, because I needed for the soils analysts, and in this case they were landscape architects, to help me to find the best soils for the green roofs. And we also had the first students coming to the site, so I started teaching students about the project on site, and I quite enjoyed doing that. And we also I also then had students as second advisor, where we did long-term research after the project was finished to look, for example, at mature trees, how they grow on roofs, and how they function. So this project was the sort of first breeding ground for me about thinking about science and the importance of science in a scheme like this. This is just another image of the project. And then another image that we did all the usual stuff. We did all the design, we did all the sketches, we did all the specs, we did all the stuff one does. On top, we looked at the durability of the materials we used, how they would weather. So I had tests being done on weathering. What kind of wood do we use? Is the wood poisonous? Is it not poisonous for the children play areas? Are there nails in it or not nails? How do we do the fixing? So all the sort of basics a landscape architect does. We looked at how the plants over the time of the year would actually grow. I've seen upstairs people looking at charts. I saw in one of the studios today looking at the autumn color patterns, the spring patterns. So we did all that. What you are taught, we actually then tried to practice. But when I was doing this, I was thinking, hey guys, that's not enough. This is another project I did after the Potsdamer Platz with my mentor. She's a very now old landscape architect who's been in practice for 50 years. And we did this work together. It's also an intensive green roof in Berlin. But when I was doing all this, I was thinking, hey, is this actually environmentally friendly? Because we're putting in a lot of energy, we're putting in a lot of material to actually create these features. It needs lots of water. So I was thinking when I went into full-time teaching, well, we need to measure this. This is not enough. We need to really, we all talk about green roofs. It's going to be the healer. I said, well, I really want to know. And is this the right city to actually have green roofs? Because is it an added-on technology? And obviously, I got lots of criticism particularly in Germany, where green roofs has been originally from, with Switzerland. It was sort of devised in the 70s, really, and it was used for car parks to cover them up so they could be used as gardens and so on. But I always had that question, is it really sustainable? So with that in mind, we sort of started our research methodology. And I said, okay, we have Vancouver downtown, and we're going to look at Vancouver and see how we could reduce the stormwater runoff in the city of downtown Vancouver. And also, how could we reduce the energy demand and the CO2 emission? Because our mission was, we wanted to measure the environmental benefits green skins, and I'm going to talk about that in a minute, actually have in a city. How could we mitigate that? So we chose, I asked the city government to give me maps. And these are very special maps. These are used by the police for the drug trafficking to check where they actually track traffic. So when you zoom in on these maps, you can see every stone on the roofs. These are high-resolution, high-end photographic aerial maps, very sophisticated. Normally you don't get them, and I asked and I said I need it for environmental benefits. It's really safe. I'm not into drugs. I want to use it in a positive way. So what we did was I said we're going to take a piece of the downtown core and we're going to measure all these issues. So I chose a site which had all the different building typologies in it. High-rise, medium-rise, and low-rise buildings, as you can see on this section here. And to give you an idea, this is the whole downtown of Vancouver. And we're just looking at 20 hectares of that downtown. So what we did was, the first thing we did was to find out how is it used? How is this area used? So we went to every apartment, and it took a long time, to look how is it either commercial, residential, office, hotel, townhouses, parking, church space, whatever it is, and made this map so that we knew what was actually going on the site. The second thing we looked at, and we simplified it in this diagram on the right, we looked at what areas were specifically commercial and what areas were specifically residential. With that knowledge, and the knowledge of calculating all the roof areas, all the facade areas, and all the floor areas of all those buildings, we were able to calculate the CO2 emission of this 20-hectare area from the electricity and the gas. How did we do that? we asked the companies to send us all the gas bills of each building. So we were able to calculate with that how much energy actually was consumed by each of those buildings. I'm not going to go into detail. It was a lot of number crunching. For that, we used Energy 10 method. That's one of the methods. There's many. Ecotect, Energy 10 is one of them. It's a simulation program where you can actually generate these figures, and that would be another lecture to explain that. I'm not going to do that. But what this program does, it gives you a specific simulation, what is actually the output. So when we looked at the result, I'm not going to go all through the figures, just to give you the two main figures. The energy that area needed for heating and so on, cooling, and what was going on was 512,000 gigajoules per year. And the CO2 emission, and that's quite stunning for me, was 21 million tons a year, just the 20-hectare site. So we were a bit shocked about these sort of figures and thought, well, it's about really time that we do something about that. So the next thing we looked at is green versus gray. We looked at the site, which part of the site is actually covered by roofs and has an impervious layer, and which part of the site actually has a connection to the soil. And we found that only 12% of the site had a connection to the soil, and 88% was impervious. So what we did next was we calculated in the area all the facades, all the roofs, all the streets, and all the green levels, and to calculate how many hectares of space we had in each. And with that knowledge, we were then able to calculate the stormwater runoff. The stormwater runoff, we used the TR55 or the CN method. The CN method is the curve number method and the crop coefficient method. The curve number method measures the impervious or perviousness of the soil, and the crop coefficient method that calculates the evapotranspiration rate of the plants. Sorry, it's a difficult word. And so with that, together, we developed these formulas. One of my research students spent 2 years on devising a formula methodology to calculate with that together with the coefficient and what kind of plants we're actually going to use on the roofs, we could calculate the stormwater runoff. And I put this into perspective for you looking at the site. So the rooftops together was 56,000 cubic meters a year, and the street level was 88,000 cubic meters a year. So that you understand what that actually means in volume, just the roof area was 20 American football fields, not German football fields, not soccer fields, American football fields, so the area of 8 hectares. And the runoff of this roof was equivalent to 22 Olympic swimming pool stadiums of stormwater runoff. That would be 56,000 cubic meter of water. This is actually the stadium in Beijing by Herzog and de Meuron. And we just used that image because I thought it was very attractive. So how did we achieve, and with that knowledge in mind, how could we achieve the ideal city? What could we as landscape architects now do to mitigate these problems? We were thinking, what could be the solution? And we thought we need to look at green roofs, green walls, and green streets. But we need to look at them holistically in a combination. Not just a bit here, not just a bit there, but at the whole thing. Because they only work best combined. So what we did next was we calculated, using those methodologies, we calculated what that impact would have. And for that, we used the Seattle Green Factor. The Seattle Green Factor was originally invented in Berlin in Germany. It was called Biotopflächenfaktor. It was then developed further in Malmö in Sweden. And then the Americans in Seattle got hang of this and developed the Green Factor. The Green Factor specifies for an area of land, if you have a certain amount of that greened up, then it would be beneficial or would have an environmental benefit on the plants. And that amount can be calculated by looking at different kinds of greening up. For example, using a green roof, using different kinds of plants, and also the soil depth, or it's not working anymore. Anyhow, I have to shout. No. And the soil depth, I'm sure you can hear me, the soil depth had also had a big implication on that. So it was really important for us to try that out, because it was a research which had been done before and where we knew that it would work. So what we tried to do was we took the site as it is and we greened 30% of the flat roofs. And then we also greened 15% of the facades and 30% of the streets to find out how much we actually could reduce the runoff. And with the 15% on the facade, we could reduce the runoff by 6%. With the extensive roofs, we could reduce the runoff by 4%. The reason why that is lower is because the facade, more water can actually percolate down, and it will percolate down faster than on the roof. It will stay there more in the position. So it's a physical issue, physicality issue. And the third one, for the streets, 3% runoff. So overall, with these interventions, if we would introduce those, we could save 13% of the runoff would be reduced just by these small incentives like the green roofs. To give you that in the pools again, this would be 57 pools overall, and we would reduce it by 7 pools. At least we had only had 50 pools instead of 57. So we thought that was also a very good aspect and a very good way forward to think about this. The next thing we looked at was the energy demand and the CO2 emission. Using these interventions, we could actually reduce the energy of the facade by 3%. And we could reduce the CO2 emission by 5% because of that, because we don't have to heat so much. With the extensive roofs, we could reduce it by 6% and 7% CO2 emission reduction also because of that. So we found out overall, using these interventions, we could reduce, using the Seattle Green Factor, 9% of the energy we could reduce and 12% of the CO2 emission. If you think about that in the million tons I was explaining to you before, that's a good deal, we thought, for a start. And then we thought, in Vancouver, we want to get more aggressive. This is not enough. We want to put on top of the research which has already been done, we want to not do the same and apply it just. We want to do more. And the idea behind this is to do this to get the policymakers in a city like Vancouver to act. Because with the numerical figures, they are able to persuade the governments to make it into a law so that everybody has to use those. Because currently the Seattle Green Factor is only used on public buildings, not on private buildings. And we are interested that all the buildings, all the new buildings needed to have that, and if possible also a retrofitting of the old buildings. So we introduced on top our bit of green technology. In this one, we wanted to use photovoltaic panels which produce electricity directly, and we wanted to use thermal panels which produce warm water. So these two together, combined with the other three, we wanted to add this on and see what we came up with in the end. So we added on 30% of green technology on the roofs and 25% on the facades, plus another 10% on the facades of greening. And the reason why we can't do more is because on the north side of the buildings, the north side, the greenery of the facades won't grow as much. What that then had, the impact that had was that on top of the 6%, we would get another 3% of runoff reduction on the facade areas. And we would also, on the facade areas and the green roofs together, reduce the energy demand another 8%. So that had a big impact. And on top of that, the photovoltaic and the thermal, 5% electricity reduction and 22%, which is a big amount, heating demand reduction on the buildings. So with these sort of interventions overall, we realized that it would have an impressive impact on any city. So the next thing we were doing, we were dreaming about this and photoshopping how we would see Vancouver, the ideal city, being created. We made some of images just for us to see how that would work, the facades being greened, the roofs being greened, or the roofs being used like here for urban agriculture. I'm going to talk about that in a minute. So that was sort of our first mission. Then we said, okay, that's Vancouver. But how does this work in other cities, and how does the climate actually influence the green roofs? And
this will work better for you.
okay.
There you go.
Okay. Don't have to shout so much. That's good. So how would that influence green roofs? So we were sort of thinking, let's try to apply this to other cities. And what we were looking for is a city which had a completely different climate pattern, because we wanted to be sure that what we were actually researching made sense in the larger picture. So what we did was we chose a city called Kelowna. And Kelowna is about 400 miles to the east of Vancouver. It's a desert. It's in the middle of the Rockies. It's very hot. And it's got a very different climate. And while we were there, we were sort of thinking, okay, because this figure crunching was so much, we're going to specifically this time around just look firstly to see if it has any impact on the green roofs and see what will happen to them. So what we did was we chose another map from the government and did the same procedure as in the last scheme, where we measured it and we looked at the buildings. And this time around, we found out it was literally the same situation as in Vancouver. There was a bit more greenery, but generally it was also, even though it was a small town in comparison to Vancouver, quite a lot of impervious surface. And the reason was because there was so much car parking in the downtown. And that obviously made so much impervious surface. And so the same situation again. So when we applied our research, just recap quickly what extensive and intensive green roof means. Extensive green roof means a very shallow soil depth, 10 to 15 centimeters, no irrigation, sedums, small plants, mostly plants which can store water a lot. That's extensive green roof. No maintenance, maybe one time a year weeding of the plants. Intensive roof means large soil depth, irrigation, which means energy again, and also you can grow literally everything you like, from a tree to a shrub. So just to specify these issues briefly. And what we did then was look at the climatic pattern of Vancouver and Kelowna. And what we found was the following situation, that in Vancouver it was raining obviously much more than in Kelowna, and in Kelowna it was raining less, but the evapotranspiration rate, the yellow bar, because of being hotter, was even higher in Kelowna. So that made us think, this could be a problem with actually doing green roofs. So the next slide explains the pattern in Vancouver. So this is the weather pattern in Vancouver. And in the winter month, it rains a lot. And in the summer, it literally rains none. But in the summer, the plants, extensive, intensive green roofs, need the most water to survive. So that was an issue for us. So how did we mitigate this? So we were thinking the only way we could, for a policy for the city to recommend this, would be saying, okay, either you irrigate 54 millimeters a year on top, and you can have a really thin soil depth, or you increase the soil depth and keep some of the winter moisture, or you leave the same soil depth and you put in water tanks, sort of like drainage elements, which can keep some of the water. So to make sure that there's enough water for the drought in summer. Then we looked at Kelowna and we realized it doesn't rain much at all. And we still have the same issue. Even because of the higher evaporation rate, the plants, both the extensive and intensive, would need more water. So the only way we could then recommend green roofs in Kelowna was that we said, okay, we only green 44% of the roof. So and that's what we work for, is if a policymaker wants to make this a policy, we couldn't recommend him to say, okay, you need to green every roof. It's not going to work. Only 44%, and the rest of each roof, the roof should be used for harvesting the water, and that water should then go on the 44% so that the roof can survive. With this methodology, I'm just trying to explain to you how important it is to actually do these numerical figures. So when you design a green roof, it's not just there just because it's sustainable. There are areas it's just not going to work. So these are the sort of issues I'm trying to address to you, that if we really want to be thorough in what we do, we really need to understand the science behind this. So this dream idea, which we've drawn up here, is never going to work with the climate pattern we have in Kelowna. So the only way we could suggest it to the policymakers is that all the water from the car parks is swaled, cleaned, and then pumped up, which again costs energy. Then you could have that effect. By that I mean you have to be really careful with your assumptions when to put, for example, a green roof in a situation. So it is much more complex than designing forms and shapes and really understanding those. You need to add on the scientific aspect and understanding the knowledge. And obviously not everybody of us has the time to do this, but if you're not sure, we need to go out to people who know and who can help us in this situation. So the next one was looking at Shanghai. And Shanghai is very different, and I will explain that in a minute. We again got a map, but this time around, because of the block structure in Shanghai, they are much smaller. They are 2.3 hectare in size, so we had to use a different formula, but in the end of the day, it worked the same way. So the same procedure, 12% and 88% is impervious. So we had the same, literally, to Vancouver. The difference now is that the climate in Shanghai and Vancouver are literally the same. It rains in both cities nearly the same amount. But now is the issue. Just to remind you, this is the Vancouver graph. In winter it rains intensively, in summer it doesn't. And then on top, this is the Shanghai graph. It doesn't rain as much in winter, but it rains a lot in summer. When the plants need the most water, that's when the green roofs really need it, if you particularly do an intensive green roof. So what these graphs show, how that is interwoven, how the climate and how other aspects is interwoven with the plants. So basically what that means is for Vancouver, we would need to recommend the policymakers, for example, you need to still irrigate 54 millimeters, but in Shanghai, you wouldn't need to irrigate at all. And then the top roof runoff in Vancouver, the stormwater runoff would be reduced by 22%, while in Shanghai it would be reduced by 29%. So you would even have a better runoff rate there too. When you look at the intensive green roof, you would actually even have to irrigate more in Vancouver, 133 millimeters, and still no irrigation in Shanghai. And you would actually reduce the stormwater by 40% in Vancouver and even higher by 57% in Shanghai. So basically what these figures show to us that, for example, Shanghai would be an excellent place to do green roofs and green interventions and green facades on all these other things. So not every city is the right place for this kind of intervention. With this theory, I'm just trying to explain to you, so when we use the term sustainability, we need to be really careful and really understand the system before we use it. So I think there's not every city is useful for green roofs. For example, Vancouver, I think, also has a problem in summer, particularly when it comes to intensive green roofs. So if we want to employ, for example, green roofs in Vancouver, we need to harvest water so that they can be actually irrigated. So these implications have then implication on other things like water harvesting and so on. So with that, I'm just trying to explain to you how important it is to look at the systems holistically. Currently, we are also looking at green streets. And if you ever have the chance, go to Portland, see Tom Lipton. Tom Lipton's work is really advanced in this field because they had so many problems with the stormwater in Portland. They developed and devised all these swale and rain garden systems. And I took my students there last year, and they really appreciated this visit. And that inspired us in the lab to look at our own streets. And in Vancouver, we have a density policy. It's called the eco-density policy. And what it does is it takes the back streets, the back lanes, and all the former garages on the back lanes are going to be made into more flats to accommodate all the increased population which is going to happen in Vancouver. And with that updating, there will be more green roofs and there will be more stormwater. So we are researching, and this is our watershed area, we are researching how we could actually accommodate and put the water back into the natural cycle on site. And we had two scenarios. One scenario, at the end of the road, we have these sort of rain gardens and the water is swaled into them. Or the other scenario was that we proposed to have these green strips, so kind of swales, so the water velocity, the water speed is reduced in the storm event, and a lot of it percolates already in here, and then the rest is drained into the soil in these smaller rain gardens. So we currently wrote a research paper on how that would work out and how the figures are. Basically, why I'm showing you that is we really need to look at these things holistically and understand all the links between them. Now, how does that go with my teaching? How do I use this research to introduce it to the students? So last year, I did the second time the intro studio, and the idea behind this studio was the usual stuff they have to learn in the first studio, all the skills, sections, plans, and everything. And I'm teaching in the master level, and we have students coming from all over the place, and some of them have never drawn. So it is quite a tough studio for people who have not had an education in architecture or landscape architecture before. And then I came in and I said, well, this is not enough anymore. You need to learn the systems from the start. And the reason why I tried to introduce this is because if we don't make them aware in the first 2-3 years about it, it should be part of the whole process to learn about the science and the real understanding of the holistic systems. So I looked at the food security issue in Vancouver, and we chose a site in the downtown, the red site there, and we proposed an inner city community demonstration garden project. And in this project, I programmed the food production, places for dwelling, and greenhouse, and a cafe. And the idea behind this was that the students in the first semester also had to learn about architecture, that they actually had to design the buildings, in a sense, not obviously specifically like architects, but they had to get an understanding between the inside and the outside to make them aware how important that process is, because it also has to do with sustainability in the sense, for example, of harvesting the water on the roofs. So they had to do all the typical standard analysis, which we all do when we do a project, and on top I asked them to look at systems. And I asked them, for example, to look at the food system and analyze it how it is now, how things are actually come to Vancouver, how they are distributed, how is the food distributed, and how much waste it actually produces, and so on. And they came up with these diagrams. And then I asked them on top to look at a way how they would see the food distribution could be improved. So they came up with this diagram that at all the different stages, the material should be composted and so on. They should be locally produced. There shouldn't be so much energy being wasted with vehicles to transport things. So they were starting to get a sensitivity and an understanding of to how the environment could be, with these sort of simple, sort of logical thinking process improved without technology, without even green roofs, just by thinking locally in a sense of local production and what actually the area one lives in can do. And I brought you 4 projects just to give you an insight what they then produced. For example, Ivy here, apart from producing the production beds, she created this huge glass house, which was not just a glass house, but it was also a funnel to harvest water, which then was partially used for the irrigation and was also partially used as a stream in the garden. Because the critique, which is always happening in Vancouver currently, is that the community gardens which happen there and the food production areas all look messy and they're architecturally not sound and the public is not happy about them. So we as landscape architects can use our aesthetic education in that and improve those areas. And that was sort of the idea behind this. The second one was Sarah, for example. She designed this cornfield, and the corn was used in a bakery to bake local bread. And she was even thinking about in the section, and that's pretty good for a first-year landscape student, looking in section how actually the building functions with the relation to the landscape and all these kinds of aspects interrelated. And I thought that was something we all need to sort of think about today when we design. Or Zhang Cheng here, she used the water harvesting as an atmospheric sort of water feature on one hand here in her section, but she also used it for her sort of irrigation system on the site. In my studio, they are not allowed to draw with the computer. And the reason for that is because it's maybe the only studio they can. And they're allowed to do Photoshop and all these things on the side, but when it comes to drawing, all their drawings need to be by hand so that they can get an understanding for the skill and learn the fast sketching for the development of their methodology in sketching. And this is the final one by Jing Sun, who developed this sort of grid system and this sort of module system and used that for her architectural expression and also devised this little diagram here looking at water and how it could be harvested in a certain way. And what you have to remember, this is in the downtown core of Vancouver. It's seen really clearly here. These are high-rise buildings. So they had to look at the shadow patterns and how that integrated. They had to look what kinds of plants they could actually grow in this area. So look, it was a very sophisticated project for an introductory studio. So I wanted, as a last point, just briefly talk about how do I practice what I preach? How do I integrate this knowledge in my own research, which I'm doing in my own practice? So my lab is currently starting to set up a practice again. I registered in Canada now, and so I thought, how can I introduce this knowledge, this science knowledge, in my experience as a landscape architect? So last week we handed in this competition in China with an architecture team which was working from Sydney and India and ourselves working in Vancouver. And the idea behind this master plan was not the slick design and the sort of green spaces we created. I said, well, that's not enough to my architecture colleagues. I said, well, we can't hand this in like that. So we added a sheet on and we did all the calculations for the area so that what we were dreaming of, or the roof gardens, or the outdoor garden areas, that there was actually enough water to irrigate them. So we got the data from Jiangpu district outside Shanghai to calculate it all through. So the actual runoff from the roofs and how it would be used on the site. So 54% would be retained on the extensive roofs, 37% would be used for the irrigation on the site of the gardens, and only 9% would be runoff. So we wanted to really be sure that what we were dreaming of here, or the project we were doing, was actually functioning. So my sort of hypothesis behind this is that when we design, this is sort of my sort of conclusion, is that as a teacher, we need to make science accessible to students, and we need to make it accessible from the first semester onwards. It needs to be integrated into the curriculum for them to understand that that is really important for the thoroughness of the sort of work they do. And I think for us as practitioners also, research in depth is really important, particularly numerical results. And I think with that we can sort of create much more rigorous landscape interventions instead of just doing it without these kinds of thoughts. So I just leave you with that, and thank you very much.